to one and all. Myself, Dr. Lakshmi Devi, Associate Professor in EEE Department of SP College of Engineering, Tirupati, welcomes you all for the Day 4 session of 5-day Faculty Development Program, Recent Challenges in Power Systems. We SV colleges renowned in terms of administration and infrastructure, where we have 8,000 plus students both at UG and PG level. We can proudly present we have backed some number of placements in 1,000 MNCs. We run our institutions on the motto education to better society. EEE department is strong, plenty sum of experienced faculty and students where we turn our team towards individual growth. As part of development, we initiated this 5-day FDP program during this COVID pandemic to ensure our safety. I feel much privileged to introduce our guest speaker, who is a renowned person who is very much strong enough in MPPT techniques in photovoltaic systems. I proudly introduce our today's resource person, Dr. D. Lenin sir. Dr. D. Lenin sir is presently working as Professor, EEE Department, Rajiv Gandhi Memorial College of Engineering and Technology, Andhra Pradesh, since 2006. He has done his PhD in the field of power factor correction converters from JNTU University, Kakinada in 2013. Sir has 15 plus years of teaching experience where he covered both UG and PG levels, and sir actually involves in R&D activities, which shows his keen interest towards research. He is a professional member in IEEE and life member in ISTE. Sir has published plenty sum of journals in SCI and 10 SCI index journals and 22 Scopus index journals and 9 IEEE and Springer conferences. This shows Sir's keen interest towards research. Dr. D. Lenin sir has received grants under RPS scheme and STTP schemes around 10 lakhs. Sir also participated in Hackathon 2019 Smart India contest as a project mentor at Udaipur under Ministry of Railways, Government of India. Sir received numerous awards as Best Paper Awards, and Sir has also organized conferences at JNTU University where on recent advances in electrical engineering conducted at JNTU University Anantapur. Under his guidance, Sir has 6 research scholars which are pursuing their PhDs and 24 PG students who have completed their projects. Sir's fields of interest includes MPPT for solar photovoltaic systems, utility grid with renewable energy sources, power quality issues in power electronics converters, electrical drives, digital control of electrical machines, and estimation of machine parameters. Thank you, sir. I feel much privileged to call your profile, sir. Thank you so much.
Thank you.
With your permission, I just want to give some instructions to the participants, sir. Just a minute, sake.
Yeah, sure, ma'am.
All the participants are requested to mute your mics and turn off your videos to save the bandwidth of other participants and to avoid the technical glitches. For all the participants, e-certificates are going to be provided from tomorrow. As it is a confined generation procedure, we may be unable to provide at a single day provision. So we will provide it in within 3 to 4 working days from tomorrow. For any queries, you may contact us at any time. We have a Telegram group where you can message us. Last 20 minutes of the session has been planned for queries session. If any of the participants has questions, they can post their questions in the chat box. If any participant has any queries, he can drop his queries. Kindly cooperate with us to make our event success. Thank you. Lenin sir.
Sir, ma'am.
I welcome you on behalf of SV College of Engineering, EEE Department, sir. Thank you for your immediate acceptance, sir. Thank you.
Thank you, ma'am. Thank you, ma'am.
I am handing the session to you, sir. Please continue.
Welcome. Thank you, ma'am.
Welcome, sir.
First of all, I would like to thank the management and the principal and head of the Department of SVCE organized this 5-day FDP program with a successful manner. And I will extend my thanks to co-conveners Dr.V.Lakshmi Devi Garu and Dr. Ramakrishna Reddy to invite me as a today resource person. and all delegates and participants, a very good morning. Madam, shall I start the technical session?
Yes, sir. You can, sir. You can.
Yeah, sure, ma'am. Madam,
Yes, sir. It's visible, sir.
is it visible? Yes, okay.
Yes, sir.
Thank
It's
you, ma'am.
visible.
Thank you.
Yes, sir.
Okay, thank you, ma'am. So very good morning to one and all. Today I am going to discuss maximum power point tracking techniques for photovoltaic system. So these are the outline of this today presentation. First, I am going to discuss mathematical model of photovoltaic cell, and I extend the discussion to the converter topologies, and also I am going to discuss the various MPPT technique controllers, and finally I am going to discuss the brief discussion about the practical implementation of MPPT algorithm by using digital controllers. So before we are going to discuss the main topic of our today presentation, just I want to do some small introduction regarding about our title. So we know that the familiar of renewable energy system, in that the photovoltaic energies became a promising alternative source, and also the processing and the principle of the photovoltaic system is nothing but which is converted into light energy to electrical energy when the photons strike on this suitable semiconductor device. So why here we prefer the photovoltaic system? Because which is having so many merits such as cleanness and a little maintenance and no noises. So the photovoltaic system, the output power depends upon the atmosphere condition, which is nothing but solar irradiation and a temperature. So when the output power depends on atmospheric or weather condition, then the output power is always regularly oscillate. To maintaining the regular power in output side, we concentrate about the maximum power point tracking system here. That is a reason mainly we are focusing on maximum power point tracking control to extract the maximum power from the PV arrays. Maximum power point tracking is used in the photovoltaic system to maximize the photovoltaic array output power irrespective of the variation of temperature, irradiation, and the load characteristics. So first of all, I'm going to discuss the mathematical model of the photovoltaic cell. Here I'm going to consider first the ideal photovoltaic cell, which is consisting of current source and a diode connected in parallel. Here the external current is nothing but the difference between the current flows through the diode and the photon current. See here very carefully, whatever the amount of current flows through the diode, it is exponential form. Based on this expression, here I am going to conclude that based on the characteristics, the photovoltaic cell behaves nonlinear performance or nonlinear characteristics. See here the characteristics which gives the information of the photovoltaic cell. We need the sufficient illumination intensity. When the illuminations became dark, then the corresponding current, see here the characteristics, the corresponding current will be very, very less.
Lenin, sir, sorry to disturb. Can you please expand the presentation mode, sir? Slide. Is it possible to expand, sir?
Right now.
Yes, sir. Thank you, sir. Thank you.
It's okay, madam?
Yes, sir. Now it's okay, sir. Okay, sir.
Okay, ma'am. Okay. So when we are going to applying the illumination intensity is very less, based on the characteristics is clearly observed that the current of the photovoltaic cell it is very, very less. Otherwise, it is approximately equal to 0. And voltage also is become very less. When I'm going to increase the light intensity or sufficient intensity to the photovoltaic system, then the corresponding current will be increases, and voltage also varies very little bit. The same concept I explained in open circuit PV cell. The external terminal is kept open here, so no current flows through the external circuit, so that the external current I is become zero here. See, where it is clearly expressed in the equation based on the characteristics. See here, when I'm going to using the photovoltaic cell with open circuit, the voltage will be appear across the open circuit is a maximum, whereas the corresponding current is become zero here. So when the current is become zero and the corresponding voltage is become maximum, the output power is become P is equal to IV is become always zero. And moreover, based on this discussion in open circuit PV cell, the current is become to zero. Whatever the quantum of voltage is available across or appear across the output side, that I called as maximum voltage or open circuit voltage. So when the current will be become zero, whatever the voltage appear across the output side, it is a maximum. Similarly, for short circuit PV cell, the external circuit I connected here, the short circuit. So the total amount of current will flow through the external circuit here. So the current is maximum, whereas the corresponding voltage is become zero here. See the characteristics also here. Then we are going to applying a sufficient illumination of the short PV cell. The current will be flows through the external circuit is maximum, is represent here the dot here. The corresponding voltage is become zero here. So in this circuit configuration also, knowing of the voltage and the current parameter, here I am going to calculate the power is become zero. In both the cases, one thing I will make conclude that the power is always become to zero when you are going to operate in open circuit or when you are going to operate PV cell in short circuit. The power is always maintained is zero. This is one of the drawback of the PV cell when you are going to operate in short circuit or when you are going to operate in open circuit of the PV system. So to overcome this drawback, here I connected the resistive load across the external circuit, which is RL. Then I connected the load circuit in external in PV system. Then the load line concept is come to the picture here. See the characteristics of the IV characteristics of the PV system here, PV cell. So depends upon the value of the RL, this dot will be moves on the curve. With the photovoltaic cell with the sufficient illumination, then see here this is a dot line. The current will be which is having some existence value, and the voltage also exists some value. So no doubt here the power also it will be exist. It is clearly observed that here we are providing the resistive load with some value. The current never become to zero, and the voltage never become to zero, and the power also never become to zero. So here, if I am going to adjust the resistive load is equal to 0 ohms, it's a dead short circuit, then the current is become a maximum is nothing but short circuit PV cell. If I am going to remove this RL, then the voltage is become maximum and the corresponding current is become to zero. So based on the variation of the RL, then the load line will be changes and the corresponding power also change. So the power is nothing but here IB. We know that the IS current is an external current. It is nothing but the diode current minus photon current. So here substituting in the power equation, here the condition for the maximum power, when we are going to derivative the power with respect to voltage is equal to 0, then it is become a maximum power. So this is the practical equivalent circuit of photovoltaic cell, which is consisting of the current source, diode, series resistance and shunt resistance. Here, I'm going to explain what is the importance of the series resistance and shunt resistance, then how it will, the value, how it will be. So when the temperature will be varies, then it's make a serious problem which can be modified, includes the shunt resistance. So the importance of this shunt resistance, it is going to protect the photovoltaic cell during the variation of the temperature. If I'm going to provide the low value of the resistance in shunt resistance, then it will be, which causes a power loss. The photovoltaic cell causes the power loss, providing the alternate current path in light generated current. Here I'm going to provide the shunt resistance, provide the very low value. The huge amount of current will flow through this path, then automatically the power loss will be increases. So here that is one of the drawback if I am going to provide low value of the resistance. So I'm going to ensure that shunt resistance must be always high as comparatively series resistance, so that here you are going to avoid the power loss of the PV cell. And moreover, the effect of the shunt resistance is particularly more at low irradiance. This is one of the drawback also. If I am going to adequate or increase the shunt resistance value, the effect of the shunt resistance is particularly more at a low resistance. When the systems operate at lower irradiance, the oscillations around the maximum power will be increased. So keeping on mind this principle, so here we have to provide the resistance value appropriate to concentrating with the power losses as well as the oscillation point of view. In series resistance, if you are going to increase the series resistance value, the voltage and the current density will be reduced in output side. So in ideal cases, how it will be the series resistance and how it will be the shunt resistance means, the series resistance will be always zero in ideal case and the shunt resistance will be infinite in ideal case. So coming the right side of the slide, here the output voltage of PV array, as this is a cell, equivalent circuit of equivalent electric circuit of photovoltaic cell. When I'm going to connect it in series and parallel combination, then it's become a array, PV array. So this is the equation represent the output voltage of PV array is the output current of the PV array. Here the NP is represent n number of series parallel combination of the photovoltaic cell. So with the help of this equation only, here we are going to calculate the voltage and the current of the PV array. So the next parameter is nothing but fill factor. So fill factors is nothing but it is a ratio of maximum power by the product of output open circuit voltage and short circuit current. The fill factor which gives the information of the optimization of the maximum power. The fill factor also can calculate through the graphical method. See here with the help of the IV characteristics and PV characteristics. Here I identified the maximum power point. Based on that, I construct the squareness of the solar cell. In this characteristics, I represent area A and area B. So the fill factor is nothing but it is a ratio of area A and area B. Here the fill factor generally, the optimal value of the optimal range of the fill factor is always 0.7 to 0.85. This range will give the optimal maximum power of the photovoltaic system. Here the fill factor will be increased when the area B will be reduced. From these characteristics, I clearly explain. area B, the area of the B will be increases means ensure that the fill factor will be reduced. Once the fill factor values is reduced further, then the oscillation around, it is going to allow the oscillation around the maximum power point. Similarly, if the area A will be reduced, the area will be reduced, also the fill factor will be reduced, and it is going to allow the oscillation around the maximum power. So that what I am going to ensure through this graphical method with the help of the characteristics, here we have to maintain the area based on the optimal range of fill factor with the help of either atmosphere condition control or with the help of the load control. So that here we can maintain the fill factor with the optimal range, which gives the resultant the excellent performance of the maximum power. So next I'm going to discuss the effect of irradiance and the temperature on the cell characteristics. So basically photovoltaic cell which is having a two physical quantity of input, one is irradiance or isolation. When the irradiance will be increased, if the irradiance is increases means how the photovoltaic system performance in terms of current profile and voltage profile. Here, based on the characteristics of IV characteristics, the influence of the irradiance of the photovoltaic cell. If irradiance increases, see the characteristics, the current will be increased rapidly, whereas the voltage will be increased very slightly. Similarly, the influence of cell temperature on the cell characteristics. When the temperature increases, the current will be slightly increased, whereas the voltage will be reduced. See here. So this is one of the reason the observation of the voltage and the current during the day. In midday, the power will be very lost because of the photovoltaic systems reach the high temperature. The voltage will be reduced and the current will be slightly increased. The product of this B and I, it's become very less. And moreover, the effectiveness of the temperature is very less here in voltage and the current as comparatively the irradiance. That is one of the reason the most of the researchers and engineers, they have to use irradiance variation for observing the external parameters of the photovoltaic system, mostly. So whatever I explained in the earlier slides, the photovoltaic system, the same system I simulated also through MATLAB Simulink environment. I observed that IV characteristics with a constant temperature. See here, I tested the characteristic, IV characteristics with the help of the low irradiance and the high irradiance. I applied low irradiance to the PV system. See here, the current will be very less, whereas it is going to maintain the sufficient voltage. Similarly, when I apply the high irradiance, the current will be increased here. The voltage, see here, the variation of the voltage is very little bit. The same analysis I applied with a different irradiance. This is the characteristics of IV characteristics of photovoltaic cell with a different irradiance value. So when I am going to increase the irradiance value like this, the current will be increased from minimum to maximum. See the boundary of the variation. When I'm going to vary the irradiance, the boundary of the variation is very huge in current profile as comparatively the boundary of variation is very less in voltage profile. Right. So the corresponding PV characteristics at constant temperature with low and high irradiance. See the characteristics, power characteristics is very less as comparatively when I'm going to applying the high irradiance, the power will be maximum here. Okay. The same analysis I applied to the with a different irradiance and I observed the PV characteristics through simulation. So the power will be increased when I increase the irradiance value. Here I am keeping the constant irradiance and varying the temperature. I observe that the IV characteristics in PV system. When I am applying the low temperature, see here the current will be less, whereas the voltage will be increased. So temperature, when I am going to applying the temperature, varying the temperature in PV system, the current is directly proportional, whereas the voltage will be inversely proportional. At low temperature, the current will be very less, whereas the voltage will be high. Similarly, for high temperature, the current will be increased slightly, whereas the voltage will be reduced rapidly. The same analysis I applied to with the different temperature conditions. See here, the variation, the boundary of the variation of the current is very, very less as comparatively the boundary of variation of voltage. So based on this discussion, what I'm going to conclude that when I'm going to varying the irradiance in the PV system, I taken as the current profile. Why? Because the variation boundary will be very large. If I'm going to maintain a constant irradiance and I'm going to vary the temperature, then I'm going to consider the voltage profile for analyze the PV system. Why? Because the range of the variation boundary will be very large. So depends upon the requirement of the external side or application, which parameter we have to control, whether we want to current profile strongly or voltage profile strong. Based on that, we have to choose the physical parameter control here. The most of the researcher and most of the engineer, they choose only irradiations rather than the temperature because of they want the huge variation of the current. Even one of the external parameter such as tracking efficiency, it is also mostly depends upon the current profile. It is not depends upon the voltage profile. It also depends voltage profile, but the effectiveness of the voltage is very little bit as comparatively current. Even you can search in any IEEE transaction papers or elsewhere papers or any reputed journal papers, most of the authors or researchers or engineers, they may use the variation of the irradiations as compared with the temperature. This is the corresponding PV characteristics, constant irradiance with varying the temperature cases. So this is the clear observation of the effect of temperature and effect of irradiance. See here, when I'm going to increase the temperature, the power will be dropped out linearly. So when the temperature will be increased, the power will be dropping. What is the reason behind the power will be dropping here means because of the huge amount of voltage will be reduced and a little bit current will be increased when changing the temperature. So that is the reason here the power will be dropping out when increasing the temperature. Similarly, see the effectiveness of the irradiance. When I'm going to increase the irradiance, the power will be increased linearly. Because of the reason is the both voltage and the current are increased, so that the power also increase here. So this is the characteristics behavior of effect of temperature and effect of irradiance. So one thing I'm going to ensure that based on the above discussion, The output power is purely depends upon the atmospheric condition, such as temperature and irradiance. We can't expect the temperature and the irradiance are maintaining as a constant. It is always changes. It depends upon the weather condition, which gives the resultant is the power will be vary. But our requirement is we need a regulated power, otherwise the constant power. Because of that reason only, here we go for the maximum power point tracking. So maximum power point tracking, I can simply explain a single line statement, which is to extract the maximum power from the PV system. That's all. A single line statement simply, what is my maximum power point tracking? Which is to extract the maximum power from the PV system. It is going to extract the maximum power from the PV system. Sir, here how you are going to track the maximum power? They are the two components. One is mechanical component and another one is electronic component. Coming to the mechanical component, the mechanical tracking mechanism using DC motor. The mechanical tracking mechanism using DC motor, how it will be worked out means, but it depends upon the sunlight direction. Here we have to rotate the panel with the help of the DC motor. This is the one of the way to track the maximum power. Clear? Similarly, for the next design of the solar panel with the anti-reflection coating, it is purely depends upon the material, the selection of the material, the selection of various silicon material, also to improve the maximum power. But the second one is more expensive. If I'm going to buy a silicon material with a low property of the power, it's around 50 rupees. Whereas the same material with an anti-reflection coating, the cost will be more than 300 for single watts. It is more expensive. And also the first mechanical tracking mechanism also, the maintenance is very, very difficult. Knowing of this drawback, here we move to electronics component. It is a very simplest one. You can operate a number of times and also which gives the excellent performance of the maximum power. This method, with the help of power electronics converter, here we are going to track the maximum power. See, this is the characteristics, how we are going to calculate the maximum power. This is the short circuit current, the corresponding voltage will be 0. This is a short circuit voltage and the corresponding power current will be 0. So the variation of the temperature and irradiance, I got this characteristics curved shape. It's a nonlinear characteristics. From this nonlinear IV characteristics, I marked the maximum power. This maximum power operating point, the corresponding voltage I called as the maximum voltage for corresponding maximum power. This is a corresponding current IPM and maximum power current. The simple equation here, the Pmax is equal to Vmax into Imax from the generalized equation of P equal to IV. So among these two components, mechanical component and electronics component, the electronics come the best as compared to mechanical. With the help of the power electronics converter, here I choose a simple basic conventional DC to DC converter. Conventional DC to DC converter classified into 3 types: buck converter, boost converter, and the buck boost converter. Among these 3, which converter is the best for tracking of maximum power? And moreover, which parameter here we have to consider to track the maximum power. Okay, I'm going to raising two questions. Among the three converters, which one is the best for operate the maximum power point tracking? And the second question is, here which parameter I want to consider most. So based on this classification of the DC to DC converter, see here, first I'm going to consider the buck converter, which is operate with the two mode of operation, switch is on and switch is off. Then I'm going to operate with the switch is on mode. See here the expression, voltage expression, VL is equal to V in minus V naught. Whereas in off mode, VL is equal to minus V naught. Based on this mathematical expression, I clearly observed that the input voltage involves only in on mode, whereas in off mode, there is no involvement of input voltage. Why here I am going to concentrate the input voltage? Exactly. My intention is I want to operate maximum power. Where it is exactly? I can operate the maximum power output of the PV system or input of the converter. So based on the converter, here I am going to focusing on the input voltage parameter to track the maximum power. This is a clear classification of the second question. Which parameter, how to concentrate more to track the maximum power. So based on the operation of the buck converter, here I conclude that the involvement of the input voltage when switch is on state, whereas there is no involvement of the input voltage during the switch is off state. So here I am going to operate the maximum power only during the on state. We can't concentrate during the off state. Similarly, considering the buck boost converter here, the same mode of operation, two mode of operation, the buck boost converter is operated with two mode of operation. During the on state, the input voltage is involved, whereas in off state, it is not involved. Here also, I conclude that if I'm going to using this converter, I can control the maximum power during the on state only. I can't control the maximum power during the off state. So this converter also is failed to select the maximum power. Coming to the boost converter here, see, during the on mode and during the off mode, in both the cases, the input voltage is involved. This is the one of the reason I select the boost converter for tracking purpose. Why? Because even during the on state of the boost converter switch, I can concentrate the maximum power, control of the maximum power, and also during the off state also, there is an effect of the input voltage. With the help of the input voltage, I can control the maximum power. So in both the cases, the input voltage is involved so that I can control the maximum power. So that is a reason here I select the boost converter. This is a clarification of the first question. Among these three, which one is the best for tracking purpose? Which converter is the best for tracking purpose? Not only having this benefit, but also the structure of the boost converter itself, it is act as a low pass filter. Yes or no? See the mode 2, when switch is open, the inductance connected in series, whereas the capacitor is connected in parallel. Just consider only the two component is a fashion of low pass filter. So the circuit between the input and output, between there is a filter circuit present in boost converter. Here I am going to conclude that I can get the output voltage with ripple free. Yes or no? So this is an additional feature having a boost converter. The circuit configuration itself, it is act as a filter circuit, so that you can extract the output voltage with a free ripple, and also you can control the maximum power with the help of the input profile, like input voltage, such as input voltage. So having of advantage of this boost converter, even in my system configuration for tracking purpose, I use the boost converter topology for the tracking purpose. So participants get the idea about these two questions, right? So coming to the various MPPT techniques, first I use integrated pulse width modulation MPPT techniques to track the maximum power. This technique, otherwise I call it as analog method MPPT technique, or conventional pulse width modulation MPPT techniques, because here I am going to using integrated MPPT controller with the help of the PI controller, anything but the conventional controller. See, this is the system configuration of the photovoltaic system with the integrated pulse width modulation MPPT method. This is the main system configuration, which is consisting of the PV array and DC to DC converter connected to the load. Here I consider the residual load only. Here the maximum power point tracking operates with the principle of maximum power theory. How it is work out? Here, whatever the impedance inbuilt with the PV array, with the help of the converter and the load, here I want to, this is an external impedance, with the help of the duty cycle, I want to match that output impedance is equal to input impedance of PV array, so that the maximum power will be exhibited. Here, the MPPT controllers generate the duty cycle, a simple duty cycle signal, which is going to match the output impedance is equal to source impedance. It's nothing but PV array impedance, so that the maximum power will be delivered. This concept only I am going to apply it in the system configuration. For the generation of the duty cycle, here I am going to calculate the V reference as a set value, and comparing with the whatever the actual voltage measured from the or observed from the PV array, this will gives the error signal to the gain controller. This gain controller, which gives the output of the control signal, and the pulse width modulation technique, which is having an input of carrier signal and the control signal, which is going to generate the output pulse. With the help of the gate drive, if anything weakness of the pulse, here I want to boost up or amplify the signal strength with the help of the gate drive. And finally, the same signal, the strengthened signal, I fed to the boost converter switch. So here the boost converter switch is the boost converter, the output voltage V0 is equal to V in by 1 minus D, where D is a duty cycle, V in is input voltage, and V0 is output voltage. So having of this output expression, voltage expression, if I'm going to control the duty cycle, then the effect of output voltage and effect of input voltage is going to change. The same relation I remodified, V in equal to V0 into 1 minus D. If I'm going to change the duty cycle, input voltage is going to change. Based on this relation, here I am going to control the duty cycle. The corresponding voltage, input voltage also affected. The affected input voltage, it will be useful for to track the maximum power of the PV system. So here this is a control block. Here I am going to sensing the input voltage and input current of the PV system. It will be given the input to the calculation of V reference. In previous slide, the V reference is a set value. Here I set with the help of the calculation here, V reference value with the help of the voltage and the current. I set the V reference and compare with the actual voltage is nothing but PV voltage. The error is the input of the PI controller. This PI controller is a conventional PI controller which gives the output is control signal. And the comparator receive the two input, one is from the PI controller and another from the high frequency carrier signal. And comparing this both signal, the pulse will be generated here. Okay. The importance of the PI controller here, the system configuration operate with the closed loop system. When the system configuration operate with the closed loop system, the gain of the system will be reduced in nature. So to improve the loop gain, this is one of the method to improve the loop gain with the help of the PI controller. In general, based on the control system point of view, PI controller, the KP, gain of the professional constant, to improve the gain of the system configuration, and the integral constant, it will be improve the steady state error, which means it is going to reduce the steady state error. So by connecting of the PI controller, here we can achieve the two benefit. One is to improve the loop gain as well as to reduce the steady state error with the help of the PI controller. Okay. So the control signal is compared with the high frequency carrier. The comparators compares this both signal, which gives the output is gate pulse. This pulse will be fed to the gate drive to amplify or to improve the strength of the pulse with the help of the gate drive. And finally, which gives the output is duty cycle. This duty cycle only I fed to the corresponding DC to DC converter switch. If the D will be changes depends upon the DPV or the calculation of the V reference, the D will be changes. Once the D duty cycle will be changes means we know that the mathematical equation D input is equal to V naught into 1 minus D. V in is change. The changing of V in, then automatically the maximum power also is going to change. Based on the adjustment of the KP and the KA value also, here we can provide the appropriate value of the maximum power. Why? Because the control signals changes depends upon the gain values. Okay. This is the one of the method to achieve the maximum power. These are the mathematical expression how to calculate the V reference. Just I shown in previous block the calculation of V reference with the help of the equation number 2. Exactly, V reference is equal to HVA into VPV into 2K by IPV. This V reference depends upon the both parameter such as VPV and IPV. Okay, right. Whereas HV is a transfer function of the PI controller. This is a transfer function of the PI controller where KP is R2 by R1 and time constant R2 into C2. Okay. So here the VAC is equal to HVA into V reference minus VP. Otherwise, the VAC, the control signal, is equal to the transfer function of PI controller into error signal. So based on the fourth equation, here I am going to generate the control signal. It is not only depends upon the error signal, it is also depends upon the HBA. It involves KP and KA values. If I am going to change the KP and KA value, the control signal will be changed. Then I can expect the change in the input voltage so that the maximum power is also can change. So this is the simulated result, whatever I explained just above. So this is the output current. Okay, it is settled around 4 point something. This is the voltage. It will be settled 15.8 something value approximately. This is the power value, the product of the current and the voltage. I got more than 60 watts. Okay, this is a system specification. I use it for simulation. I consider the maximum power is 100 watts and open circuit voltage 21.75. The maximum power, maximum voltage at the maximum power condition, it is 17.10, and short circuit current is 6.43 ampere, and the maximum power point current IMPP is 5.585 ampere. So I simulated the system configuration with the help of this specification. The available power is 100 watts, but I tracked only here the 60 or less than the 70 watts power with the help of the pulse width modulation, integrated pulse width modulation technique. And also, this is the result. When I consider the temperature is 25 degrees centigrade and the irradiance is 200 watts per meter square. Based on this result, I clearly observed that when I'm going to apply the low irradiance, so the current and voltage will be reduced here. See, the current will be less than the 1.5 and the voltage also less than the 14 volt. Power also reduced around 13 or 12 point something. So this is the clear proof of the influence of the temperature and the irradiance, right? So this is the numerical values also I analyzed with the help of the different irradiance by keeping a constant temperature 25 degrees. Here, the current will be gradually increase. See here, gradually increase when the irradiance will be increased. Similarly, the voltage also see here, it will be increased. This is the one of the evidence. If I am going to vary the irradiance from minimum to maximum, the current and the voltage will be increasing from minimum to maximum, and the power also will be increasing from minimum to maximum, right? So the photovoltaic system with integrated pulse modulation techniques having an advantage is a simplest technique. It is one of the simplest techniques to track the maximum power of the PV system. And also this is one of the conventional pulse technique to track the maximum power with the faster response. But even though the system configuration is having a disadvantage, here the voltage and the current are controlled independently by the selecting of the environmental condition. Here, when the voltage profile and the current profile are act independently, ensure that the performance of the system configuration coming down, especially in PV system. Here I ensure that the independent operating of the voltage and the current profile, which gives the result, the performance of the PV system is degraded. And moreover, it is operated with less operating point voltage, and it is going to introduce the high current oscillation also. Having a knowledge of this drawback, and I move to the next MPPT control technique to overcome this drawback, open circuit voltage method. Whatever I discussed the previous method, it is nothing but the analog MPPT controller Whereas this open circuit voltage method, otherwise it is called as computational method. The computational method is nothing but it is a programmable one. We can use the digital controller so that the complexity will be reduced as compared with the analog method. The open circuit voltage method, this is a system configuration of the open circuit voltage method. Here initially I am going to observe the open circuit to keep open the output terminal so that I can measure the output voltage at initially. Then afterwards, once we know that the output circuit voltage it is maintained as a constant value, then regularly have to observe the output voltage of the PV array. Otherwise I call it as VPV. It's fed to the open circuit voltage MPPT control block, which gives the signal to compare with the pulse width modulation with the high frequency carrier signal, which gives the duty cycle. The duty cycle is control the boost converter switch. This boost converter switch is control the output voltage as well as the input voltage is nothing but VPV. So here this is the basic mathematical equation of open circuit voltage to develop the algorithm or to develop the
Lenin sir? Lenin sir? Hello? Lenin sir? Dear participants, please wait, hold a minute. I'll call sir and I'll inform you. So just be on the line. Sir, మీ వాయిస్ వినిపించట్లేదు సార్ అసలు 3 minutes నుంచి వాయిస్ లేదు సార్ మీది. ఇప్పుడు అసలు మీరు మీటింగ్లోనే కనిపించట్లేదు సార్, ఒకసారి చెక్ చేయండి సార్. లేదు సార్, మీరు మీటింగ్లోనే లేదు సార్, లెఫ్ట్ అయిపోయింది మీది. Just for few minutes, sir is facing some technical issues. We are going to sort it out. Just for few minutes, please wait. Lenin sir? Sir, is it audible to you, sir? Lenin sir, unmute yourself, sir. Your speaker is in mute symbol.
Okay, sure, ma'am. Madam, now it is okay.
Now it's audible, sir. From 3 to 4 minutes, your voice is not audible.
Okay, sorry, madam.
Okay.
Right now it is okay, no?
Yes, sir. You can start presenting your screen, sir. You please start.
Yeah, sure, ma'am. Sure, ma'am. Thank you, ma'am. Okay. Sorry. Due to some technical problem. Okay.
As this is an online mode, we are all facing technical glitches, sir. So,
okay.
Thank you, sir. You start presenting your screen, sir. Your screen is not visible.
Okay, thank you. So, with the help of this...
Sir, your PPT, sir. Your PPT is not visible. Just make sure.
Okay. Yeah, I want to share, no? sound right?
Yes, sir. Now it's okay, sir. Thank you. Hello. Hello, Lenin sir. Lenin sir. Sir, your voice is not audible, sir.
What about the slideshow, madam? It's okay?
Now both are okay, sir. Your slide is
Hello?
yes, sir. Both things are good, sir. Your voice is audible and PPT is visible, sir. Both things are good. Lenin sir. Lenin sir, your voice is not audible, sir. Again. Lenin sir. Sir, your voice is not audible, sir. Hello. ఇప్పుడు మళ్ళీ మీరు డిస్కనెక్ట్ అయిపోయారు సార్. కాల్ చేస్తే మీరు డిస్కనెక్ట్ అయిపోయేటట్టున్నారు. మీరు ఫోన్తో కనెక్ట్ చేసినట్టున్నారు సార్ నెట్ని. సో మీరు కాల్ చేస్తే కాల్ కట్ అయిపోతుంది. నేను మెసేజ్ పెడుతుంటాను సార్. ఇందాక కనెక్ట్ అయింది, మళ్ళీ ఎందుకో వాయిస్ మిస్ అయింది. మేబీ మీకు ఆ స్పీకర్ ప్రాబ్లం ఏమో. ఓకే. Sir is facing some technical issues. Within two minutes, sir is going to rejoin, please. Lenin sir.
Madam.
Now you are audible, sir. Just start presenting your screen, sir.
Okay, I will upload. No.
Yes,
Madam, now slide is visible, madam?
Yes, sir. Yes, sir. Your voice is also audible, sir. You just continue, sir. Thank you.
Okay, ma'am. Thank you.
Sorry for the interruption, all the participants. Now, sir is ready to continue his presentation. Please.
Yeah. Okay. So this is the system configuration of the open circuit voltage with the maximum power point tracking. So this is a mathematical equation to develop the duty cycle or to develop the algorithm to control the maximum power point. Where K is the voltage constant factor, which is nothing but it is a ratio of VMP by VOC. The range of the K values is 0 to 1 because the VMP is varies up to the maximum value is equal to VOC. The best value of the K is varies from 0.71 to 0.8. So when we are going to maintaining the K value between this range, you can get the optimized output power value. This is the I developed algorithm. Here I initialize the K value based on the value 0 to 1. and also I fix that K value from 0.71 to 8.8, and I start the measure the open circuit voltage. Just I kept the external terminals kept open, and I observe the open circuit voltage, and I model the operating voltage using V model is equal to K into VOC. With help of the adjustment of K value, it will be depends upon the VMP. Then the calculated VMP is reached to V model. Then the algorithm is going to stop the it is going to stop so that the maximum power will be reached. So this is the flow chart of the open circuit voltage algorithm. Here I measure the VOC output voltage and initialize the K value is the range of 0.71 to 8.8. So here I am going to checking the V model is equal to K into VOC. If the V model is equal to VMP, the program is going to stop the running process. Otherwise, it is going to change in the K value. In existing techniques of the open circuit voltage, the most of the researcher is kept the constant value of the K to operate this open circuit voltage algorithm, and is getting the at one fixed maximum power because of here the fixing the K value. But in my proposed technique, here I provide the range of the K value so that here I got the optimized value. I'm not getting the exact value. Here I got the maximum optimized and maximum power with help of the variation of the K value. This is I proposed in this technique. Okay. So this is the results, the power results, voltage and the current. See the current significantly increase as compared to the previous technique, and voltage also increase. Then the product of the voltage and the current. Now see the earlier technique is around 60 watts. Now it is increased by around 70 plus. With the irradiance is 100 watts per meter square at the constant temperature is 25 degree. The same system configuration I simulated with help of the irradiance value is 200. Then the voltage and the current will be reduced, and the power also here reduced. See, the voltage will be reduced and the current also here reduced. Then the power is also reduced here. This is a numerical observation. So when I am going to increase the irradiance from low value to high value, the current will be increased from low value to high value, and the voltage also increased from low to high value, and the power also increased from low to high value. So based on this analysis, the previous MPPT techniques which gives the maximum output power around some 68 something, here with the 1000 irradiance. In these techniques, there is some significant improvement of the maximum power. It's around which gives 71.84. But in these techniques, it's having a drawback. Initially, if you want to observe the open circuit voltage, here we have to isolate the external circuit. The major drawback of the open circuit voltage, even though it is very simple, even though it is operated with faster response, and also the result is having a less distortion, but the major drawback is we have to isolate the external circuit from the PV system when we are going to observe the or measure the open circuit voltage. That is a major problem of this. So due to this, sometimes the K will be performed very poor. It's a non-flexible constant of the K. Okay. To overcome this drawback, I want to avoid the isolation of the external circuit and internal circuit, and also I bring into constant value of the K with a flexible manner. Here I move to the next control techniques is nothing but short circuit current method. Here this is the same system configuration, just I modified the MPPT controller block. Earlier it is open circuit voltage. Now it is a short circuit current method. The short circuit current method, just I replace the resistant load with the help of the short circuit current, short circuited at initially to measure it is useful to measure the short circuit current at initially, not in real time application. Just beginning at initial stage only. Here I am going to make a short circuit to observe the short circuit current. Then afterwards I am connecting the resistive load. Here I observe the regularly IPV. But here there is no isolation between the external circuit and the PV system. Okay, right? So this is one of the disadvantage overcome to the previous method, right? Here this is the mathematical equation I use it to develop the algorithm. So IMP is equal to K into ISC. So where K is the current factor, constant factor. This current constant factor, we know that the range, the adjustment of the operating convert from the 10% to 90% of the ISC. Why? Because based on the IV characteristics, I already explained, when I am going to changing the irradiance value, we can observe the huge variation of the current as comparatively voltage. That is the reason behind. Here the operating range I am going to vary this K value from 10% to 90%. Okay, whereas I provide the K value in open circuit voltage, see very carefully, 0.7, it means 70% to 80% around. Why? Because the variation boundary restricted 70 to 80% in open circuit voltage, whereas in short circuit current, the elaborated range variation from 10% to 90%. It is also one of the advantage, and it is also one of the beneficial feature of this short circuit current MPPT method. So having of this equation, I developed the algorithm. So initially I provide the K value, the range from 0 to 1. I provide the range from 0.1 to 0.9 value in terms of value. And I measure the short circuit current with the help of the replacement. I make a short circuit. I provide the low resistance value of the RL load. And regularly I calculate the IMP so that I can adjust the preset value of the K with this fourth step until the calculate IMP reaches to I model, which means until it is reaches the maximum power, the K will be changes appropriately. Okay, so this is the algorithm flowchart. Measure I short circuit current and initialize the K value so that I can calculate the I model current is something but K into ISC. Here the changing K, here I fix the value, the range is from 0.1 to 0.9, which means 10% to 90%. When the IMPs is become equal to I model current, then it is come to stop, which means it is reaches the maximum power. Okay, until it will be changed the K value, and again it will start the process until it reaches the maximum power. These are the corresponding result of the power and the voltage, the current. See here, one thing here observed very clearly, when I am going to constant the short circuit current, the voltage is oscillated huge variation as comparatively current. Due to the voltage oscillation, the power also here oscillated here. See, during the transient interval, and it is settled. It take so far long time, and it is settled. And also there is some significant improvement in tracking power also, maximum power also. Right? These are the result I observed. At the irradiance is 100 watts per meter square with a constant temperature of 25 degrees centigrade. This is the result under the low irradiance value with fixed temperature. This is the numerical analysis. It is clearly observed that see there is some significant improvement in the power. Earlier it is some 71 point something. Now it is 78.18. Due to we have a huge variation of the current constant factor, and moreover here we can't isolate the external circuit from the PV system. Okay, correct? But there is a problem with this record very high impedance. Yeah, it is real, true. So whenever they have to measure the short circuit current to protect the PV cell, here we have to provide the high impedance. That is one of the drawback here, right? And moreover, in open circuit voltage, current is operate independently, whereas voltages operate dependent. Similarly, in short circuit current, the short circuit current is operate dependent, whereas the voltage is operate independent. I earlier discussed, if the voltage profile and the current profile operate independently, means which gives the result is a poor performance in tracking of PV system. In these two techniques, open circuit voltage and short circuit voltage, one of the parameters is dependent and the other parameter is independent. It is also one of the drawback in both MPPT technique control. That is the reason I identified this drawback. That is the reason I moved to the next, but P and O is otherwise I called as power based MPPT technique. Earlier it is individual voltage, individual current based. So there is a drawback. Okay, right? Because one of the profile is operate independently, whereas in PERDAP and observe method, it is otherwise it is called as power based MPPT technique, which is both parameters are dependent parameter. With the help of this technique, here I am going to overcome these two drawbacks of earlier methods. Okay, right. So this is the system configuration. Just here I am going to observing the voltage as well as the current fed to the P&O MPPT technique. Okay, to drive the PV system configuration. Right. This is the basic mathematical equation. We know that a maximum power is nothing but the derivative of the power with respect to voltage is become equal to 0. The derivative of power is nothing but P of k minus P of k minus 1. Where P of k is the present value, P of k minus 1 is the previous value. When the previous value and the present values is become to match, then resultant will be 0. Then dP by dV is equal to 0, so that the maximum power condition is satisfied. Okay, right. By adjusting of the P of k, I used to change the profile of voltage. See here, V of k is equal to V reference plus or minus del V, where del V is a incremental voltage or decremental voltage. Okay, otherwise I simply said that PERDAP voltage. PERDAP is nothing but a small changing in the voltage, that's all. So having of the small changing of our PERDAP voltage, here I am going to modify the new value of the V of k. Okay, which is changes the P of k, where P of k is equal to V of k into I of k. Here the power equation P of k is equal to V of k into I of k, the both profile voltage and current are dependent, but here I used to take to vary the voltage V of k, but I never use the I of k to change, which means I'm not using the change effectiveness of the I of k. Otherwise, it is unsolved or unthreshold value of the I of k. Here I fix the current value. Here I am going to change the voltage. Ultimately, the P of K also change. So based on this concept, here I am going to adjust the V of K so that the P of K also change. Then dP by dVk until it is reaches to 0 or until it is reaches to maximum power. This algorithm is repeated the same process to changing the further voltage, either incremental way or decremental way. Okay, right? Yes. So this is the algorithm flowchart. Here I measured voltage and the current, and I calculate the power P of K equal to V of K into I of K. And now I check the condition whether it is 0 or not. P of K minus P of K minus 1. If it is yes, sorry here the arrow mark will be representing wrong. Right. If yes, then straight away it is going to return. If it is no, then it is going to check the process. Okay, they are the 4 cases to increase or to decrease the further voltage. Okay, right? In left hand side, this is in left hand side, it will take a part of, see here, it is clearly from the PV characteristics. So this is the maximum power region. Here I take a 2 part. 1/4 is a left side is a 1 part, and a 2/3 right hand side is another part. Okay, right? Here in flowchart, V of K minus V of K minus 1 is equal to 0. See, if it is yes, it is add. If it is no, it is decrease. So minus del V and plus del V. This will be take the left hand side portion of the PV curve, this part. This part of the flow chart will take care about the right hand side portion of the PV curve. Clear? Okay. There is a incremental, there is a decremental in right side. Similarly, there is a incremental, there is a decremental in left side portion also in PV curve. Okay, right. So by increasing and decreasing the further voltage, here I am going to updating the P of K, which is almost equal to the present value of the K, so that my chances if become P equal to 0, we can reach the maximum power, right? This is the method to apply it to the system configuration to track the maximum power. So I initialize the duty cycle between 0 to 1 and measure the Kth and the K minus 1, present and the previous value of the voltage and the current and power. Okay, right? Here in 5th step, see the condition. The first one, case 1, dP is less than 0, dV is greater than 0. I request to decrease the duty cycle. Similarly, in both dP and dV are lesser value, I request the duty cycle to increase, which means further voltage is reduced, further value is increased here. Okay. Similarly, in 7th step also, I call up to increase the duty cycle when the condition is dP is greater than 0 and dV is greater than 0. Okay, when dB is greater than 0 and dV is less than 0, I request to reduce the further voltage so the duty cycle will be reduced. Okay, so processing this 4th step and return to the go to 3rd step until it is reaches the maximum power. Okay, right. So see here the case 1, case 2, case 3, case 4, step 5, 6, 7 and 8. In both the cases it will be lesser value than positive. See here 1, it will be increased towards to maximum power. Okay, right? Second one is minus, it will be decreased towards to the, right? See here the third one is also increased. 2 and 3. There's a minus sign, action minus sign. It's minus del V. This is a minus del V. The further voltage will be reduced here, case 2 and 3. Whereas case 4, the further voltage will be increased. Okay, right? This is the one of the best method and simplest method to track the maximum power. These are the results. And I'm going to using the P&O method. The oscillation also here see. as comparatively in the individual voltage and individual current method. Okay. So coming to this, the sudden changing of the irradiance value, I observed that it is also somewhat quickly reach the steady state, right? When I'm going to increasing the irradiance value, right? So this is a voltage, this is a current, okay? Product of these two, I got the power value, right? So this is analytical representation of when I'm going to vary the irradiance so that the output voltage will be increased. Similarly, the output power also increase linearly. This is the effectiveness of the irradiance. Okay, right. So this is an analytic evaluation of the compare the previous three techniques: P and O, short circuit current, and open circuit voltage. The red color line is a better performance, which gives the better performance as comparatively these two: open circuit voltage and short circuit current. Okay, right. So this is a numerical analysis of the P and O method. Earlier, I observed that some 79 point something, here the 80.4. There is a significant improvement in maximum power. Standard temperature condition is nothing but 1000 watts per meter square and 25 degrees centigrade. Right? Here, I increase the putter voltage 1%, 2%, 3%, 4%, and 5%. I observed that which gives the more oscillation at 5% when I select the putter voltage at 5%. So the P and O method in general, which gives the maximum power, is 80.4, 1% of the putter value. When I'm going to increase the putter value up to 5%, is reduced the maximum tracking efficiency or tracking power. The reason behind this, when I'm going to increasing, listen very carefully, when I'm going to increasing putter voltage, it is going to introduce the more oscillation around at the maximum power point. That is the reason behind the tracking efficiency is going to reduce. If I am going on increase this putter voltage further, definitely the tracking efficiency is going to reduce. Which means, indirectly I am saying that there is a oscillation introduced around the maximum power point. That is a major drawback of the P and O. That is a major drawback of the P and O. Why? Because the current is unsolved. I'm not considering the current value. Just I fix the current value. Only I'm going to changing the voltage so that the power will be reflected. The power will be changes due to the changing of the voltage by fixing of the current. Even though I consider the current and voltage, both are independent, both are dependent, but I'm not taking care about the current profile. I'm only taking care of the voltage so that the power will be varies, depends upon the voltage. Okay, so when I'm going to put up the voltage, I increase the put up voltage of the voltage, the oscillation will be increased around the maximum power point. This is a major drawback of the P and O. Okay. So on the extend my analysis with the help of the load variation also. Okay. Keeping the putter and the standard temperature at the standard temperature condition is constant. Just by changing the load variation, then how it will be performed the tracking efficiency. Okay, here at point at 9 ohms, it is almost matched with the input impedance. Okay, so that which gives the maximum tracking efficiency. If I'm going to increase in the resistance value of at load side, it is not matches with the PV impedance. So the tracking efficiency decays slowly. See here the curve. This is reduced slowly. Right? This is the effectiveness of the load variation. How the tracking efficiency will be present. So when you are going to match the external resistance to the PV impedance, the tracking efficiency became a maximum. Okay, right. What is the tracking efficiency? Tracking efficiency is nothing but how much power we are going to utilize from the available. Simple, that's all. That is how much power we are going to utilize from the available power of PV system. Simple. It's nothing but tracking efficiency. Right? So I clearly mentioned that when the MPPT, this is a drawback, when the maximum power is reaches, the power P&O methods allows the oscillation around the case of constant voltage pattern. Oscillation around the maximum power. Moreover, it's performed poor efficiency due to non-flexible of environmental condition. The fixed pattern. To overcome this drawback only, here I modified this. I call it as improved P&O method. Improved P&O method, which is having a benefit feature as it is P&O, and also here I'm going to considering the current profile also with the help of the adding the additional loop. It's nothing but irradiance loop. Okay, see the same here. I am going to observing the two profile of voltage and the current effect to the algorithm similar to P&O, but thing is here I split it into two portions of the PV curve. That is center power P of C, and the P of K is one of the DP1 curve. This is a DP2 curve is a maximum. P of K is a previous and the present curve. Taking these two, I analyze it here with the help of this two curve. See, the derivative of the power is equal to P of K minus P of K minus 1 is a generalized equation is similar to P&O. The P of K, dP of K, I modified the same equation with the help of the previous graph here, dP1 and dP2, dP1 minus dP2 of K, right? So dP1, I read it, okay, P of C minus P of K, P of C minus P of K. dP2 of K is nothing, P of K minus PC of K is P of K minus 1 minus P of C. Okay, so knowing of this equation, I substitute in the above equation number 1. I got the final equation 2. Here clearly mentioned that dP of K is equal to 2 PC of K minus 2, P of K minus P of K minus 1. Okay, right? Yes. Right. So here when this parameters become equal to 0, okay, then it reaches the maximum power. That mathematics, see the flow chart. This is as it is P&O flow chart. Here the additional parameter, additional loop I consider this loop I call as irradiance loop. The irradiance loop, it is going to unsolve the current profile. Okay, earlier we directly calculate the power with the help of the voltage, but here we are calculating power with the help of the voltage as well as current. Here, the unsolved problem of the current, here I consider in improved P&O, so that the efficiency of the tracking of maximum power will be improved with the help of the improved P&O technique. Okay, and also it is reduced the oscillation, but the thing is it will take more time to reach the maximum power. Why? Because the processing speed will be reduced as compared to P&O due to additional loop of irradiance. Okay, right? That is a main drawback. These are the algorithm similar to P&O, right? Just only we are adding the C, K and K minus 1 present and previous. Now we are going to considering the center power also here. Okay, right? The remaining algorithm procedure is similar as it is P&O, right? The results also see that there is an improvement in the tracking efficiency because of the adding of the additional loop, irradiance loop, right? But the only drawback is it will take more time to reach the maximum power because due to the additional loop of the system configuration, right? So comparatively, this is a analytical evaluation of the various MPPT techniques. See the improved P&O is which gives the best performance as comparatively other technique, right? Here also I analyzed the putter voltage, changing putter voltage. There, see very carefully, there it will be varying with a linear fashion. Where I involve the current loop, see here the graph, it will be standby with almost constant, see 80.7, 80.44, 80.17. This is the result when I adding the irradiance loop in PN loop. Okay, so the oscillation will be reduced due to the maintaining of the power tracking efficiency, even though I increase the putter voltage, right? So based on the numerical analysis, based on the graphical method, I conclude that the oscillation will be reduced when I include the irradiance loop, which means I consider voltage as well as current to adjust the power P of K. Okay, right? This is one of the evidence. Okay, right. And also I validate the load variation. Okay, with the same resistance value. Okay, here earlier it is some 80.1, now it is increased. Okay, right. Right. But thing is, what is the drawback of this improved P&O processing? It will reach more time to, the maximum power point tracking take more time to reach. To avoid this drawback, here I propose adaptive P&O method. Adaptive means that external system parameter is going to adopt with the P&O parameters. Otherwise it is called as duty cycle P&O method. Duty cycle. Instead of varying of voltage and current, or instead of varying of these two profile voltage and current, here I am going to change a single parameter such as duty cycle. If I change the duty cycle, not only it is going to reflect the voltage, and also it is going to reflect the changing in current also. Right? Listen very carefully. The earlier method, with the help of the P&O and with the help of the putter voltage, I change the voltage profile, and with the help of the additional loop, I change the current profile so that the power will be changed. Clear? So changing of this voltage and the current profile with the help of the putter and the irradiance loop, it is very complex. And moreover, it will take more time to reach the maximum power. To overcome this drawback, I'll leave it the two parameters variation. Instead of the two variation of the parameter, I consider only the duty cycle. When I consider duty cycle, indirectly it is going to change the voltage as well as current. Okay, so that the reaching of the maximum power also is very short duration. Quickly it is reaches the maximum power point also. Okay, right. Here I propose the constant or fixed adaptive putter. Okay, which is having one of the input of the P&O technique. This is also P&O method only. Only thing is, here I am not changing the voltage and current directly. With the help of the duty cycle, indirectly I am going to changing the voltage and the current. That's all. Right? Also, a very beginning slide, I explained the subtitle, converter topologies, boost converter and inverter. Here I am bringing to the system configuration to connect to the grid through boost and the PV system through boost and inverter. Okay, right? Here the inverter circuit, I use the simple sinusoidal pulse width modulation to control the inverter operation. Okay, right? To track the maximum power, here I use the adaptive putter observe method here. So this is the PD curve. It's a duty cycle. It is similar to PV curve, isn't it? It is similar to PV curve. PV curve now I am going to replace by PD curve. right? Earlier, directly I'm changing the voltage. Here, indirectly I'm going to change the voltage with the help of the duty cycle. That's all. Okay. It is not only it is going to change the voltage in boost converter. For example, in boost converter, if the voltage will be increases, what about the current profile? Automatically, it is going to reduce. Which means the duty cycle is going to reflect the changing of voltage as well as current, right? Based on this concept only, here I applied the duty cycle concept. When I am going to changing the duty cycle, indirectly the voltage and current is going to change. Okay, right? See the condition, the dP by dt is greater than 0. It is going to conserve the positive slope portion, okay, of the PD curve. When PD and by dd is less than 0, it is take care about the tracking of in right side portion. Okay, in both the cases, the adjustment will be towards to maximum power, Okay, our intention is this condition with the changing of duty cycle to bringing this closer this condition, so that earlier it is minimum. Now I am going to change the duty cycle and bring you to conditions equal to 0 and reaches maximum power. Similarly here also, the condition will be greater 0. By adjusting of a duty cycle, I am bringing to and making equal to this and reaches maximum. That's all. Okay, this is the expression, is plus or minus. See here. So d of k and dk minus 1, the present value is equal to previous plus or minus this value. The numerator portion dp of k by dt is equal to 0. Okay, then it reaches maximum, which is nothing but the present value of the duty cycle is equal to previous value of the duty cycle. Otherwise, we can say that not only dp by dt is equal to 0, otherwise we can say that d of k is equal to d of k minus 1. Okay, right. So this is the condition of the greater value of the dp by dt value. This is an incremental, this is a decremental value. Okay, right. So this is incremental, this is the decay. This values will be decreased, then it will be reaches the maximum. This value will be increased, then reaches will be maximum. So by varying of the duty cycle with the fixed rate or with the fixed step size, okay, then it reaches the maximum power. So based on this concept, see the algorithm step number 4. See d plus c into slope. The slope is I consider either 1 or 0. The slope is considered as either 1 or 0. Most of the time I consider as plus 1, or most of the time I consider as minus 1. Okay, right? Where c is the changing of duty cycle, changing of the incremental changing of the duty cycle. Where c is the incremental changing of the duty cycle. If c is changes, then d will be like d of k will be changed, right? So based on this concept only, I tune this algorithm to bringing the maximum power with the less oscillations. Okay, right. So see here the flowchart algorithm. I measure the V of k and I of k, and I calculate power, and also I calculate the dp. Okay, right. I check the condition here. If it is yes, okay, then move to left side. It is going to slope is become 1, and add the incremental value of the duty cycle and fix the output duty cycle and save the earlier power and the present power and calculating and repeat the process until it reaches the maximum power. If the case is failed, then it is no, then the slope will be minus 1. Okay, it is otherwise it is decrease the duty cycle and save the result the present value of the duty cycle d of k. The corresponding power will be changes here. Okay, this is a positive incremental, this is a negative incremental. That's why I compared slope is nothing but minus slope. Okay, this is a minus slope, this is a minus 1. Okay, right. Let's see is the incremental step of the duty ratio. How we represent del V per voltage, similarly here del C, that's all. Okay, see here, it will be reaches very quickly. Voltage, see the voltage will be reaches quickly, is around 0.01. current also reaches very quickly, and the power will be increased here. Right? Okay. But when we are going to fix the duty cycle, there is a drawback during the low irradiance. If you are going to operate with the low irradiance, then oscillation around the voltage will be increased as comparatively current. Once the voltage oscillation increases means, I conclude that power also oscillated here. See, due to voltage oscillation, power will be oscillated. Whereas the current, see, it will be operated in smooth manner. Okay, right. This is one of the drawback. See, I clearly project the result during the low irradiance value. See, there is oscillation in the voltage and the power here. Whereas when I operate with the high irradiance value, see here, there is no oscillation. So what I conclude that with the adaptive P&O method, it is more suited well for when the irradiance operate with the high value as compared to low value. Okay, there is a drawback in this because at low irradiance value, there is oscillation around the maximum power, right? To avoid this drawback only, again, I propose a modified technique. Yes, this time is almost okay. Here, earlier I fixed the K value, isn't it? Now see the C value, C of K, this equation C of K, where C is an incremental duty cycle. Okay, earlier I fixed it, but here of K means is a variable, invariant. There I fixed the invariant, C value is invariant. In this algorithm, here I fixed the C value with the variant factor. Here automatically it will be varying, incremental decremental of the switching frequency. See, where C of K is the present incremental or decremental switching duty cycle, where C of K minus 1 is the previous switching cycle. See, just here I'm going to given the freedom of the incremental decremental of the duty cycle. Either you can increase or decrease, depends upon the adaptation of the system configuration, right? So because of this reason, due to this changing of incremental decremental of the variant of the incremental decremental of switching cycle, even I applied the low irradiance to the PV system, I observed that there is no oscillation in the output side. See that clearly here. Just in same algorithm, just I modified it here. Online tuning on C of K. Online tuning of C of K. Here I am tuning the C of K. Is a variant factor. Incremental duty cycle is variant. Otherwise, variable step size and curve. Okay, right. See here, at oscillation will be minimized in the standard temperature condition, and also see that when I am going to operating with low irradiance value, there is no oscillation in the voltage and the current, and the power also there is no oscillation, and also it reaches very quickly. Okay, it is very lengthy program. Even the discussion will be very simple, but the implementation is very horrible. Right. Okay. These are results and discussion, and I verified with the various different condition of the irradiance value. Yes, there also I observed that there is no oscillation around the MPPT with the help of the power and the current and the voltage graph. Right. And also the tracking efficiency is improved to 91.25. Okay. The same, see here, the adaptive, see here very clearly the analytic evaluation, MPPT technique, adaptive P&O. So adaptive P&O, which gives the best performance. See the voltage will be reduced, but the current, see here power in this, yes, power, current. Yes, the voltage and this is a power output. Okay. There is a voltage and the current will be changes. See in previous slide, here the voltage, this is a voltage. Okay, here the changing the voltage and the current here before low irradiance and after high irradiance. Similarly, here also see the current. Here the current will be reduced. Here the current will be increased. It is operate quite opposite. Okay, right? Similarly, after the higher irradiance value, see the current and the voltage. The current and the voltage is operate with the quite opposite. Okay. Anyhow, the product of the power of the modified adaptive P&O, which gives the best performance as comparatively adaptive P&O method here. Okay, right? See, this is I observed TD curve also through simulation with the help of the changing of the duty cycle, how it will be. Yes, I verified results also through simulation environment. Okay. Right. And also, I extend my analysis with the help of the load variation. Here also, the efficiency, tracking efficiency will be improved at matched almost closer value of the load resistance. Okay, right. So finally, I conclude, if time is not permitted to explain the practical. Okay. Madam, are you here? Are you there?
Actually, we are running out of time, sir. We have 10 more
Yes,
minutes.
Yeah. I will wind up, madam. I will conclude that. Okay, right?
We have number of
right.
questions too, sir. So.
Yeah.
So after your conclusion, I'll ask you the question, sir. Or else, if you want, I'll continue now.
Now I conclude, madam. Now I conclude. No problem, madam. It is very, time is not permitted to explain the hardware implementation. It is very, yeah. Okay.
Okay, sir.
Up to simulation, I will stop. No.
Okay, sir.
Okay, madam. Okay. So I conclude that the modified adaptive P&O method is the best P&O method as compared to the previous method here. Okay. So we discussed here several MPPT techniques. The first one is pulse width modulation technique, and the second one is open circuit, and third one is short circuit current. Fourth one is P&O, and the fifth one is improved P&O and adaptive and modified adaptive P&O. So we discussed 7 techniques of various MPPT techniques here. Among these 7, the modified adaptive P&O method the best in all aspect point of view here. Okay, right? So the same technique I implemented through hardware implementation also. I saw used to say, if time is not permitted to explain. Okay, right? So I would like to thank to all participants, and moreover I hope to understand my presentation with this various control techniques, MPPT control techniques. It is maybe useful for to start up the research work, this basic platform of the photovoltaic system. The same system configuration I extended to grid connected system in practical implementation also, and also now I'm doing the same system configuration still further extent of islanding detection method also. That project also, yes, I grant the received. I mean, one of the colleagues with help of me is received project around 42 lakhs and from the SERB, DST SERB, the proposal. This is a basic work of this grand project. Okay, right? If time permit, I will extend my presentation somewhere. I will explain this neatly, the extended work also. Okay, thank you. Thank you to one and all. Okay, right. Ma'am?
Sir, thank you, sir. You have given a very elaborative session in detail, sir. Thank you for your presentation. We have some queries, sir.
Yeah.
Sir, can you suggest which is the efficient MPPT method to improve the efficiency of PV cell to implement hardware? I think the answer you have given now. Modified.
Yeah. That's the last method. Yeah, modified adaptive method is the best techniques. As per my concern, what I realized around the 7 MPPT techniques, the last one is the best. And also I proved that results also numerical and graphically also, ma'am. Okay?
Okay, sir.
Right?
One more,
if any further discussion, yes, ma'am.
Range of duty cycle as output. What will be the range of duty cycle value as output?
Usually, when we are going to operate with the maximum power, here I am going to using the boost converter. The boost converter is performed well during the range of 0.5 to 1 in general. But come to the maximum power point tracking, the duty cycle range will be around 0.5 to 7 is the best. 0.5 to 0.7 the best range, right?
Okay, sir. Thank you, sir. One more question, sir. Can you, is there any specific criteria to estimate the duty cycle?
Yes. So here we have the relation of the output voltage of boost converter. Based on that, we can't bring that voltage is equal to VOC, output voltage. Why? Because if you are going to operate the output voltage is equal to open circuit voltage, we know that the power is become to zero. Keeping in mind this concept and as well as the short circuit current, when we are going to operate in the maximum short circuit, the current will be operated to maximum is equal to short circuit current, and also power is become equal to zero. By using, I'm keeping this mind of the two concepts appropriate, we have to select. That's all.
So one more from Amit Kumar sir. Which type of power quality issues arise in solar cell energy system? Let me know their solutions.
Power quality issues means here mainly conversion efficiency. It's a conversion efficiency is very less of the photovoltaic system. By beginning stage of the photovoltaic system, it will be used around some 20 to 25% of conversion efficiency. Conversion efficiency is entirely different from the tracking efficiency. Conversion efficiency is the maximum power by incident power, whereas the tracking efficiency is nothing but how much power we are going to utilize from the available. So here power quality issues become a conversion efficiency parameter. Exactly, as per my knowledge. Okay, right.
For MPPT tracking, do we need to provide VMP for different irradiance conditions or just for the rated conditions?
No, we can tune that different various conditions. No issue.
How to calculate the settling time for PV MPPT control?
How to calculate the
settling time for MPPT controller?
So here it depends upon the duty cycle. We can calculate the settling time with the help of the elaborated mathematical analysis, madam. Otherwise, through graphical is the best option, but it is trial and error. But we have the pakka evidence, to prove that the settling time with the help of the duty cycle is the best, but it is complex in mathematical analysis. That's why most of the people, they go for the graphical method with the trial and error. Yes, ma'am.
Sir, one more question, sir. What can be done for hands-on training?
Better to have to attend more seminars and FDP like this, so that we can gain the knowledge. And otherwise, we have to visit the industrials. Maybe it is useful to gain the awareness of this work.
How can I calculate the value of an inductor used for connecting the grid with inverter?
Yes. Is also there. Is a designing of the inductance and capacitor of the boost converter, and also degree of this load also. I forgot that the book material is a foreign author. Okay, I will mail it. Just inform to author to mail it.
Sir, actually, number of participants have been asking about your PPT, and any materials, if you provide, I will share them, sir.
Yeah, sure. I will sell by tomorrow, madam.
Okay, sir.
The same thing you can share to the participants. No,
okay,
no problem.
So you have some more questions. To apply the MPPT algorithm direct on the inverter of a standalone PV system.
Yeah, there is a modified converters is available in practical cases. But here I am going to using a two-stage of the converter. First stage is boost converter, second stage is inverter converter. With the help of the Z source inverter is a only single stage. Yes, but thing is the complexity will be increased in the converter part as comparatively two stage, and moreover, and the changing of the parameter profile is very simple when you are going to extending the stages as compared to the single stage. So that's why here I am going to select the two stage of the converter part of our system configuration rather than the Z source converter. Yes, ma'am.
Sir, is there any relation between solar module efficiency and module ambient temperature?
Ambient temperature, but exactly it is a material technology. I don't know. But then we are going to providing the anti-reflecting coating material. It is one of the method to track the maximum power. That I explained in a mechanical component to track the maximum power. It is goes to physics department to design the material technologies.
Okay, sir. So we have a lot of questions. You please be patient
Just
to
to
answer,
inform to
sir.
participants, just to inform to participant to communicate with through mail or through after successful completion of FTP.
Yes, sir. Sir, at constant temperature and for different values of irradiance,
Yes, ma'am.
PV values are varying linearly. But
Yeah,
if
yeah,
increase in temperature, more session because of your hardware
ma'am.
implementation, sir.
Yeah, yeah, yeah. Yes, ma'am.
Thank you, sir. Thank you very much.
Yeah, thank you, ma'am. Thank
I
you.
request all the participants to fill the feedback forms. Thank you, sir. Thank you so much.